So you test this limit. You try the x-axis and you get 0. Then you try the y-axis and you get 0. So the limit must be 0, right? Well, actually, this is wrong. This is the biggest trap in multivariable limits. In the next few minutes, I'll give you a 4-step decision tree, and by the end, you'll know whether to disprove with paths or prove with algebra, and you'll finally stop guessing about how to evaluate multivariable limits. This decision tree is our toolkit. It's the entire flowchart for solving any multivariable limit problem short of the formal epsilon delta proof. Our goal is to work through this tree, so let's start with step 1, where we're trying direct substitution. Let's say we have this multivariable limit problem. Our first step, step 1, is to try direct substitution, meaning can we just plug in the point 1, 2? Well, let's see. If we plug in 1, 2, we get 1 squared minus 2 divided by 1 plus 2. And when we simplify, that gives us a negative 1/3. Because we get a real number here, we know that the function is continuous at this point, 1, 2, and we're done. We don't have to go any further. We know the limit is negative 1/3. But what happens when step 1 fails and we get 0 over 0? If the function isn't continuous by direct substitution and instead we get 0 over 0, our next step is always trying to disprove with paths. And the rule is simple here. If we find any 2 paths that give different limits, then the limit does not exist. It's game over. So if we can show any 2 different limits, we know the limit does not exist. Let's say we've been given this limit problem where we're approaching the point 0, 0. We can see that if we try substitution, we're going to get 0 minus 0 over 0 plus 0 or 0 over 0, which means substitution doesn't work for this problem. We have to try step 2 of our decision tree, disproving with paths. And the 2 easiest paths to try are always the x and y axes. So let's try the x-axis, or the line y equals 0. If we plug that into our limit problem, we substitute 0 for every value of y. And because we're holding y constant at 0, that part of our limit drops away, and we're just taking the limit as x goes to 0. So we have the limit as x goes to 0 of this x squared minus 0 squared over x squared plus 0 squared, which of course simplifies to just 1, because the zeros drop away, we're left with x squared over x squared, that simplifies to 1. What happens if we try the y-axis, or the line x equals 0? Well, in this case, the limit simplifies to the limit as y goes to 0, we plug 0 in for x, and we're left with negative y squared over positive y squared, which of course simplifies to just negative 1. So our first path, approaching 0, 0, gave positive 1. Our second path gave negative 1, which means we found 2 different limits. They don't match, and we've proven that the limit does not exist. It doesn't matter if we can find many other paths that have a limit of positive 1, or many other paths that have a limit of negative 1. Even if we test a million different paths, and they all have the same limit, except for one path which has a different value for the limit, then because we get 2 different limits along 2 different paths, we know right away that the limit does not exist. Okay, but what about the limit problem that we started with at the very beginning of the video? In this one, if we approach along the x-axis, or the line y equals 0, this problem simplifies to the limit as x goes to 0, we substitute 0 for y, and we end up with 0 over x squared, or just 0. And if we test the y-axis, or the line x equals 0, we end up with the limit as y goes to 0 of 0 divided by y squared, we also get 0. We get 2 different matching limits, so does the limit exist? Well, actually, this is a trap. It proves nothing at all. What we need is a stronger test. So let's see what happens when we test every straight line, not just the lines y equals 0 and x equals 0, which we can do all at once using our family of lines y equals mx. You'll recognize this from the slope-intercept form of the equation of a line from algebra, y equals mx plus b. We've just dropped the plus b y-intercept and instead described every line with just the slope m, because our limit here is running through the point 0, 0, so the y-intercept we already know is b equals 0, so we get y equals mx plus 0, or just y equals mx. These are all the lines running through the point 0, 0. What we do is substitute mx for y into our limit problem. That means we're left with just the limit as x goes to 0, and we sub mx for every y in our function. When we do that, we can simplify the function here to mx squared divided by x squared plus m squared x squared, and we see that we can cancel an x squared from every term in the function. That leaves us with just the limit of m divided by 1 plus m squared. Because there are no x variables left in the function, the limit as x goes to 0 has no effect on the expression, which means that this original limit for every line is dictated by this value m divided by 1 plus m squared. And what that means is that there's no single limit, that the value of the limit depends on the value of m. So for example, if we take m equals 1, we get 1 divided by 1 plus 1, or 1 over 2. If we take m equals 2, we get 2 divided by 1 plus 4, or 2 over 5. And so we can see every time we change the value of m, we're going to get a different value for the limit. And therefore, because there's no one single limit, this one calculation is a complete proof, and we know that this limit does not exist. If we try the x and y axes, and we try the entire family of lines, and all the limits agree, and they're all giving the same value, our next step is to try a curved path. For example, maybe we have this limit. For this one, if we try substitution, we end up with 0 over 0. If we try our family of lines, y equals mx, our limit simplifies to the limit as x goes to 0 of this function. We end up canceling an x squared from each term, and what we're left with is 1 divided by 1 plus m to the 4 x squared. And if we substitute x equals 0, this term goes to 0, we're left with 1 divided by 1, or just 1. But this y equals mx tool is not the ultimate tool, not quite. Even though the limit along every straight line is 1, that doesn't mean the limit must be 1. We've only checked lines. What about curved paths? When all lines agree, our next step is to try a curve. And usually, one of the easiest curves to try is one that balances the exponents in our function. Notice that we have x squared and we have y to the 4. That means in this case, we want to test this curved path x equals y squared because it's our power match path. It's the one that balances the exponents. If we make that substitution, we're holding x at y squared, which means our limit simplifies to just y approaching 0. We've already dealt with the x piece, and then we substitute for x, y squared, and we're left with just y to the 4 over y to the 4 plus y to the 4, or 1y to the 4 over 2y to the 4, which is going to simplify to just 1/2. And that's the end of our proof right there, because we've shown that the limit of every line is 1, but the limit of this single curved path is 1/2. And because we found two different limits, 1 and 1/2, and they're not equal to each other, that's enough to say that this limit does not exist. So if we've tried the axes, y equals 0 and x equals 0, we've tried the entire line family, y equals mx, and we've even tried a power matching curved path, and all of our paths are still giving the same limit. In other words, we were not able to show that the limit did not exist by testing multiple paths. If the paths are still matching, then our next step is to try to prove the value of the limit using algebra, instead of trying to prove that the limit did not exist using paths. Primarily here with algebra, our goal is going to be to factor and then cancel. For example, if we have this limit here, if we try substitution, we see that we get 0 over 0, and maybe we've tried different paths, like the lines family y equals mx, and some power matching curved paths, and we're still getting the same value for the limit every time. That moves us to step 3 of our decision tree, which is to prove with algebra, because we can't use different paths to prove existence. Even if we try the line family y equals mx and an infinite number of curved paths, it still never proves the value of the limit. We need a path-independent method. So what we do here with this problem is we factor the numerator. We see that it's the difference of squares. And once we factor, we notice that we have this common factor of x squared plus y squared in our numerator and denominator, which means we can cancel it. And this function simplifies to just x squared minus y squared. And now we can actually evaluate the limit. Previously, if we tried to plug in the point we were approaching, 0, 0, we got 0 divided by 0, which doesn't tell us anything. But now that the function's been simplified, we end up with 0 minus 0, and we can therefore say that the value of the limit is 0. We didn't test any paths. We proved with algebra that the value of the limit is in fact 0. What we did here was we simplified on a punctured neighborhood. Limits care about nearby points, not the whole. So even though at 0, 0, the function gives this undefined 0 over 0, when we simplify with algebra, we're left with a much simpler continuous limit. We've algebraically proven that the limit is 0. The problem, of course, as I'm sure you've anticipated, is that not every function is going to factor and cancel cleanly this way. What do we do if the algebra doesn't factor? Well, that brings us to our final, most powerful tool, which is to prove with polar coordinates. To show you how we do this, let's start with this limit problem here, x squared y over x squared plus y squared. Step 1 of our decision tree, substitution, is going to give 0 over 0. If we test a bunch of paths, the line family y equals mx, and a bunch of curved paths, we're going to get 0 for every path that we test. So step 2 in our decision tree does not allow us to show that the limit does not exist by finding 2 different limits with 2 different paths. Step 3 of our decision tree, algebra, fails us here. We can't really factor and cancel anything. So we're on to step 4, which is to convert this function into polar coordinates. And these are the substitutions we're going to make to get a function that's in Cartesian coordinates, x and y, into polar coordinates, r and theta. For x, we'll substitute r cosine theta. For y, we'll substitute r sine theta. That means also that x squared plus y squared is equal to r squared. And if we're taking the limit as xy approaches 0, 0, we can convert that or rewrite that as r approaching 0. So in this particular case, we'll get the limit as r goes to 0 of r cosine theta quantity squared times r sine theta when we substitute for x squared and y. And in the denominator, because we have x squared plus y squared, we know that's equal to r squared, so we replace that value. And when we simplify the numerator, we get here r squared times r times cosine squared theta times sine theta. We can cancel an r squared from both the numerator and denominator, and that leaves us simply with r times cosine squared theta sine theta. And this now is our critical moment. From here, we start bringing in our rules for polar coordinates. We'll go through these in more detail, but if we end up with something like this, r to the k power multiplied by some function of h that's in terms of theta, and that's what we have here, in fact, r to the k power where k is 1, multiplied by some function h that's in terms of theta. As long as k is greater than 0 and h is a bounded function, then the limit is going to be equal to 0. We know that by Squeeze Theorem. Again, we'll walk through that in more detail, but there's 2 other cases. If we have a different case where the r disappears and all we're left with is some function in terms of theta, so all we're left with is h of theta and there's no r remaining at all, we know the limit does not exist because the limit depends on the value of theta. Every time we change the value of theta, the value of the limit's going to change, which means we're going to find different limits, which means the limit does not exist. And then the third case is where we're left with some function h that's in terms of theta divided by some r to the k power where k is greater than 0. This is actually the same as the first case, but if we wrote it in this form, we would say k less than 0. We would get a negative exponent here that would move that to the denominator. So when we have something in this form, then the limit does not exist because the limit blows up to some infinite value. So because our limit is this first case, we know right away that the limit is equal to 0, and we've proven that by converting to polar coordinates. Again, we had here r to the 1, so k was equal to 1, k was greater than 0, and h was bounded, this function h in terms of theta, was bounded because cosine is squared here. That means cosine squared is going to oscillate between 0 and positive 1. So we have the value of cosine squared bounded between 0 and 1, the value of sine bounded between negative 1 and 1. And when you multiply those together, you're still going to get something that's always bounded between 0 and 1. So h is bounded, k was greater than 0, and our function was in this form, r to the k times h of theta. So the limit is 0. What about that second case though, case 2 in polar coordinates? This is our old problem where we've already shown that the limit does not exist. When we convert this to polar, we end up with this function here, and the limit as r goes to 0. If we expand that numerator, we see that we end up with an r squared factor in each term. So if we cancel out that r squared value, the function simplifies to just the limit as r goes to 0 of cosine squared theta minus sine squared theta. But we know from trigonometry that that's equal to cosine of 2 theta. That's a trig identity. And notice now that the only thing left here is theta. There's no r variable remaining, which means that taking the limit as r goes to 0 has no effect on cosine of 2 theta. So this whole limit here just simplifies to cosine of 2 theta. And that, remember, is case 2 of our polar decision rule where there's no r remaining. All we have left is a function h in terms of theta, there's no r variable remaining. And when that's the case, the limit does not exist, which of course is because the result depends on theta. So if we change the value of theta, which means we'll be able to find at least two different values for the limit, essentially proving with paths that the limit does not exist. In other words, going back to our decision tree, what we're looking for when we're trying to prove the value of the limit with polar coordinates is this value here, r to the k times h of theta. If we find that, then we know by Squeeze theorem that the value of the limit is 0. But if we find simply h of theta, our limit does not exist. Or if we find this expression, but k is less than 0, such that we have h of theta divided by r to the k, that also means that the limit does not exist. This is the decision tree we want to move through in order every time we're trying to find the limit. If none of this works and we're still not sure, we really only have two other options. One is to try a Squeeze theorem proof without polar coordinates, which I'll show you next. And then our last is the formal epsilon delta definition of the limit, which we'll save for another video. Let's look at our last tool here, our Squeeze theorem proof without polar coordinates. What we're going to do here is use a famous inequality proof. Before we actually look at the limit, let's look at this inequality. Let's say theoretically here that we have some value of x and some value of y. We don't know what they are, but what we know we can say for sure is that no matter the values of x and y, when we take their sum or difference, it doesn't matter if both x and y are positive, they're both negative, or one is positive and the other is negative. When we add them together or subtract them from one another, what we're going to end up with here inside the parentheses is some negative value, some positive value, or 0. When we square that, the negative value is going to turn into a positive, 0 is going to stay 0, and the positive value is going to remain a positive. This left-hand side here, therefore, always has to be either equal to 0 or positive. It has to be greater than or equal to 0. So this is something we can always say is true no matter the values of x and y. So building from this, what else can we say? Well, if we now expand this left-hand side, we have the product of binomials here. So we get x squared and then plus or minus, depending on the sign here, 2xy, and then always plus y squared. Regardless of the sign here, the sign's always going to be the same. So two positives multiplied to a positive, two negatives multiplied to a positive, we're always going to end up with plus y squared. So we've just expanded the left side. And then continuing on, we break this into two inequalities. This sign here can either be positive or negative. We've put the positive here in our first inequality, the negative in the second inequality. So we just separated this into two different inequalities. And then from there, we're isolating these two xy terms to one side of the inequality, moving everything else to the other side of the inequality. Or another way to say that is that we've solved both of these inequalities for x squared plus y squared. Then, if we divide through both of these here by 2, we end up with negative xy and positive xy on the left, this same value of 1/2 times quantity x squared plus y squared on the right. And then what we realize is that we can merge both of these inequalities back into one by merging negative xy and positive xy into the absolute value of xy. Because of course, remember, the absolute value of xy is equal to xy, but it's also equal to negative xy because applying the absolute value to this negative xy gets rid of the negative sign and changes it to just absolute value of xy. And of course, the right-hand sides of these inequalities are already equivalent at 1/2 times quantity x squared plus y squared. So we merge these back together to get absolute value of xy less than or equal to this right-hand side. We know also that when we take the absolute value of something, it's always going to be positive or 0, which means that this has to be greater than or equal to 0. We can't take an absolute value and get some negative number. And this then is our famous inequality that we're going to be working with. So let's say we've been given a problem like this one, a limit, and let's say we went through our entire decision tree and weren't able to prove the value of the limit. Well, we can still find the value of this limit using this famous inequality. The way that we do it is by wrapping this function in absolute value. If we do that, and we compare this to our famous inequality here, then what we can say is that this whole thing has to be less than or equal to this limit here. So we've kept the limit notation the same, so that's not going to have any effect. If we then think about this absolute value as applying individually to the numerator and denominator, in other words, the absolute value of a fraction is equal to the absolute value of the numerator divided by the absolute value of the denominator, then we can see even more clearly that these things are equivalent because we kept the same denominator, absolute value of that square root. And in the numerator, we have the absolute value of xy, which we compare here to our famous inequality, less than or equal to that numerator from our famous inequality. So we're adapting our original limit to match this famous inequality. And as we do that, we know that our original limit, after applying this absolute value, has to be less than or equal to this limit. Of course, then we also know that our original limit has to be greater than or equal to that same limit of 0. Again, all we're doing here is manipulating our original limit to try to make it match this famous inequality so that we can sort of rewrite and simplify and eventually figure out what the value of this limit is. So we sort of have this matched up now to the famous inequality. What we want to realize at this point is that taking the absolute value of these square roots here in the denominator isn't going to have any effect on those roots. Notice here that we have x squared plus y squared. Well, no matter the value of x, whether it's negative, 0, or positive, when we square it, it's either going to be 0 or positive. When we square y, it has to be either 0 or positive. So when we add those two values together, the value underneath the root either has to be 0 or positive. When we take the square root of either 0 or a positive value, we'll of course end up with 0 or a positive value, which means that applying absolute value is going to have no effect. And therefore, we can drop those absolute value bars in order to simplify. And now if we look at this limit over on the right-hand side, we notice in the numerator we have x squared plus y squared, or we could think of that as being raised to the first power. In the denominator, we have x squared plus y squared raised to the 1/2 power because we're taking the square root. So our exponent rules tell us we can do 1 minus 1/2, or that these simplify to the square root of x squared plus y squared. And now what we see is that if we evaluate this limit on the left-hand side, we're taking the limit of a constant, so this left-hand side is always going to be 0. If we take the limit of the right-hand side, we can use direct substitution with x equals 0 and y equals 0. That gives us 0 for the right-hand side. And so this whole three-part inequality simplifies to this limit here being greater than or equal to 0 and less than or equal to 0. And now remember, this in the middle is our original limit except for these absolute value bars in the numerator. But remember, the absolute value of xy speaks for both positive xy and negative xy. Remember up here when we consolidated negative xy and positive xy into absolute value of xy, we can now break that absolute value back into positive xy and negative xy. And of course, our original limit included positive xy, not negative. So we know absolute value of xy can stand for positive xy. And therefore, we're allowed to remove those absolute value bars to get back to our original limit problem here in the center. And because our original limit has to be greater than or equal to 0 and at the same time less than or equal to 0, the only value it can possibly have is 0. And therefore, by Squeeze theorem, using this famous inequality, we've proven that our original limit, the limit we started with, is equal to 0. So that was a lot, but remember, it all comes down to this 4-step decision tree. We always try direct substitution first, and if we get a real number, then we're done. That is the value of the limit. If instead we end up with 0 over 0, our goal is to disprove or show that the limit does not exist using paths. We can try the x and y axes. If they both give the same value, we can try the entire family of lines, y equals mx. If the value of the limit depends on the value of m, then we've proven that the limit does not exist. Otherwise, if we're still getting the same value for the limit every time, we can try a curved path, x equals ky squared, or a power matching path is usually a good bet to try. And if through any of these steps we can find two different limit values, any two different limit values, then we've shown that the limit does not exist. If, no matter how many paths we try, we still keep getting the same value of the limit, then we can only suspect that the limit exists, but we still have to prove it. That means we go on to step 3, and our first goal is to use algebra, which usually means trying to factor and cancel. And if algebra doesn't work, then we're trying to prove by converting to polar coordinates and looking for that r to the k times h of theta expression. If we get this and k is positive and h is bounded, then we know that the limit is 0. Otherwise, if we get either case 2 or case 3 in polar, then we know the limit does not exist. And if none of that works, we can always try using our famous inequality to squeeze the limit. Otherwise, if we've gone through our entire decision tree and we still don't have an answer, then we're going to have no choice but to go to the formal epsilon delta definition of the limit. If this video helped, please make sure to like and subscribe, and make sure to check out my full Calc 3 course, linked down below.